In this video, we're going to talk about Taylor polynomials. So the motivation for this section is calculators can easily do things like adding numbers, subtracting numbers, multiplying numbers, and dividing numbers. So they can easily plug numbers in to polynomials because polynomials do a combination of those things. And the question I want to ask is, how does a calculator determine something like e to the 0.2? So a calculator doesn't know what this is exactly. What it actually tells you is an approximation of this. It tells you an approximate value. And the way it approximates this is it approximates it with polynomials. Polynomials. Those are things that a calculator can handle more easily. Okay, so let's talk about the idea and how a calculator might do this. So I'm going to draw some axes. So let's draw some axes. So an x-axis, a y-axis. Let's go ahead and draw a rough graph of e to the x. So let's say that this is our graph of e to the x. So this is f of x equals e to the x. So I want to get a feel for what's happening at 0.2. So let's say 0.2 is here. So I want to get a feel for what is the value of the function at 0.2. Well, there is a value close to 0.2 that I know how to plug it into my function and like what I will get out. If we take 0 and we plug that into the function, we know what the y value would be. It would be 1. So one thing I could do if I want to sort of approximate the value at 0.2 is I could do this in sort of the math 11 way. So this is going to be sort of the math 11 way, which is sort of the equivalent of calculus AB. So this would be sort of the first course that we would take in calculus. And in calculus part 1, what we would do is we could approximate this with a tangent line. So we could approximate it with a tangent line. So if I were to draw a picture of a tangent line now, so the tangent line would look something like this. So that is a tangent line at x equals 0. And the equation of this tangent line, I'm actually going to call it P1 of x. And I'll talk about why later. I'm calling it this. So P1 of x, and the formula for this tangent line, if I were to work it out, is x plus 1. That is the equation for that tangent line. So again, the reason why I'm taking the tangent line at x equals 0 is we know what's happening here. In a sense, I know what I get when I plug 0 into my function, and I know what the derivative is at 0. I can quickly work that out. It's also going to be 1, it turns out. So I can get the equation of the tangent line at this point. So this is a point where I have a lot of information about. Other points like 0.2, I don't have a ton of information about. Like, I don't know how to plug 0.2 into this. I don't know how to figure out e to the 0.2 by hand. So then the type of thing that I would do is I would take the 0.2, I would plug it into the equation of the tangent line, and that would give me this y value, which is close to the y value that I want. The y value I want is this one above it on the functions graph, but it's not exactly the same. So it's an approximation, maybe not the best approximation, but an approximation nonetheless. So there are two things that I want to note about this approximation. So the first is, if you take 0 and you plug it into the function, into e to the x, and if you plug it into the tangent line. So if you plug 0 into both of them, into both of their equations, these are equal because they have the same y value. Both of these y values are 1. So these are 1 because they have the same y value at x equals 0. Their y value is 1 for both of them. And the other thing that's true about the original function and this tangent line is they have the same derivative at 0. They have the same derivative at 0. both of those derivatives are also 1 here. They have the same, let me say, same first derivative. They have the same first derivative at x equals 0 as well. But that's where it sort of stops. If we were to take the second derivative of both of these, the second derivative of e to the x will also be 1 when we plug in 0. But for the line, when we take the second derivative of this line, the second derivative is actually 0 everywhere. So that's where it stops being the same. Okay, so our sort of first attempt was to approximate it with a tangent line. And a tangent line, its equation is a type of polynomial. So what I'm going to do next is the second attempt. And in this second attempt, let's try approximating with a higher degree polynomial. So tangent lines were good for us in Math 11. Now in Math 13, we can build the tools to handle higher degree approximations. So I'm going to draw a smiley face because we are now ready to handle stuff like this. That's what the smiley face is saying. All right, so in our example, let's try a higher degree. Let's try to approximate this with the degree 5 polynomial. Okay, so I'm going to begin by writing down just the general form of a degree 5 polynomial. So we might have a constant term in the front. I'll call that a naught. We might have an a1 times an x. So the a's are all constants, plus a2x squared, plus a3x cubed, plus a4x to the 4, and then plus a5x to the 5. So all these a's are constants here. So this is an arbitrary degree 5 polynomial. And what I'd like to happen is something really similar to these two properties. So I'm going to impose, so let's impose that our function, e to the x, and our polynomial sort of agree when we plug in 0. And furthermore, that the derivatives all the way up to the fifth derivative agree. So when you take the derivative and you plug 0 in, that's going to be the same in both of them. When you take the second derivative and you plug 0 into both of them, I'm going to impose that that's the same. And I can keep going like this up until I get to the fifth derivative. So usually once we get high enough with our derivatives, we stop writing tick marks. Usually the convention is we stop after 3. We write 3 tick marks, but after that it gets confusing, having to count all the tick marks. So then the notation is for the derivative, we write which derivative we're taking in a little parentheses up here. Okay, so that means the fifth derivative of f. And that's going to be equal to the fifth derivative of p5 evaluated at 0. So now that we have a fifth degree polynomial, we can impose that all of these values agree up until these fifth derivatives. We can't do more than that because if we were to take a sixth derivative or higher, the sixth derivative of this polynomial is going to be 0 again. And that won't match up with the sixth derivative of our function at 0, because that would be 1. All right, so next what I'm going to do is, so we have this general formula for our polynomial. Let's take all these derivatives, like the first derivative, the second derivative, all the way up until the fifth derivative, and then plug 0 in to all of them. So we can evaluate all of these right-hand sides. All right, so I'm giving myself a little bit more room. So I've just copied down our polynomial here. And now we need to take the derivatives. So let's take the first derivative. So the derivative of a naught is 0, because that's a constant. The derivative of a1x is going to be a1. With the next term, the 2 comes down, and I get 2a2 times x to the 1. With the next term, the 3 comes down, and we get 3a3x squared. The next term, we get 4a4x cubed. And with this last term, we get 5a5 x to the 4. So that's the first derivative. If we take the second derivative, so the derivative of a1 is 0, because that's a constant. The derivative of the next term would be 2a2. The next term would be, so the 2 comes down, and I get 6a3x. With the next term, the 3 comes down, and I'll get 12 a4x squared. And with the next term, the 4 comes down, and we get 20 a5x to the third. Okay, so we got to do 3 more derivatives, because I said all the way up to 5. So third derivative. 2a2 is a constant, so its derivative is 0. I'm going to start to do this a little bit more quickly. The next term's derivative is 6a3. The next one would be 24a4 times x. Last term, the 3 comes down, and I'll get 60 a5x squared. 2 more to go. Once we get to the fourth derivative, this is where we stop writing tick marks typically, and we write this parentheses notation. Okay, so first term is 0 because that's a constant. Next term's derivative would be 24a4. And this last term's derivative would be 120 a5 times x. And then finally, the fifth derivative would be just 120 a to the 5. Sorry, a sub 5. Okay, so we have the original function, and now we've taken the first 5 derivatives of it. So remember, what we wanted to do with this, the condition that we sort of imposed was that if you take all of these, so if you take the original function, p5, and you plug 0 into it, that should be the same thing as f of 0. This is plugging 0 into e to the x. And the same thing is going to be true for all of these first 5 derivatives. When you plug 0 in to both of them, they will all agree. So that's true for the second derivatives of both the polynomial and f of x. It's true for the third derivatives. In fact, we had written this down before. I'm just sort of reminding ourselves. So the fourth derivatives, even the fourth derivative of f, and then finally the fifth derivative. So p5, its fifth derivative, plugging in 0, and then the fifth derivative of our function e to the x. So all of those need to be the same. Okay, so on the right-hand side, I'm going to need to evaluate all the derivatives of f of x. So remember, f of x was e to the x, and it's really easy to take derivatives of this. All the derivatives of e to the x are just itself. So that's kind of nice. We don't have to do work to actually take the derivative of this. So now let's start to plug 0 in to all of these. So if I scroll up so I can look at this, if I plug 0 into p5, into my original polynomial, what survives is just the a0. All these other terms become 0. And if you plug 0 into f of x, you get e to the 0. And e to the 0 is 1. So now we know the first coefficient of our polynomial. That's a0. So overall, our goal here, let me write that a little bit better. The goal is to get these coefficients. And now I have one of them. I got a0. So now let's do the same thing with the first derivative equation. If I plug 0 into the polynomial's first derivative, the only thing that survives is a1. Everything else is 0. When you plug 0 into the derivative of f of x, well, the derivative of f of x was e to the x. Plugging 0 into that gives me 1 again. So that's a1. That's my next coefficient. So it might be tempting to think that, oh, maybe they're just all 1. So unfortunately, it's not quite that nice, but it still is pretty nice. All right, so now if we plug 0 into the second derivative of the polynomial, what survives is 2a2. I'm going to do this a bit more quickly now. If we plug 0 into the third derivative of the polynomial, we get 6a3. Into the fourth derivative of the polynomial, the only thing that survives is 24a4. And into the fifth derivative of the polynomial, we get 120a5. All right. On the right-hand side of all of these, we just keep plugging 0 back into the derivative of all these derivatives of e to the x. Will just keep giving us e to the 0. So that's just 1. So that's kind of a nice coincidence. E to the x is really special. That's why we keep getting the same value on the right-hand side. In general, that will not always be the case. Okay, so in these last few, let's isolate for the coefficients. So a2 is going to be 1 over 2. a3 is going to be 1 over 6. a4 is going to be 1 over 24, and a5 is going to be 1 over 120. So now, do you notice a pattern in these denominators? Pause the video for about 30 seconds and see if you can determine what is the pattern in these denominators. 4, 3, 2, 1, pause the video. Pause the video and really think about what you think the pattern might be in the bottom. All right, so let's go ahead and talk about it. So the pattern is the denominators are all factorials. This is 2 factorial, 6 is 3 factorial, 24 is 4 factorial, and 120 is 5 factorial. And if I even go higher than that, this is technically 1 over 1 factorial, because 1 factorial is 1. And even up here, it's actually 1 over 0 factorial. It turns out that 0 factorial is defined to be 1. Okay, so all of these coefficients have this factorial at the bottom. So why is that happening? Why the factorial? So the reason this factorial is showing up is, let's just focus on one of these terms, like the x to the 5. Think about what happened to that term step by step. First, the 5 came down. Then in the next step, the 4 came down. In the next step, the 3 comes down and gives us 60. And in the next step, the 2 comes down. So overall, we end up multiplying 5 times 4 times 3 times 2 to get the coefficient in the front. And that is 5 factorial. So that's why the 120 ended up being a factorial in disguise. All right, so at this point, we have all of these coefficients, so we can approximate e to the x with our 5th degree polynomial. So a naught was the constant coefficient, it was 1. The coefficient of x is also 1. The coefficient of x squared is the a2, that's 1/2, so we'd get x squared over 2 factorial. In fact, if I really want to be precise, I could write the x being over 1 factorial. And then we would get x cubed over 3 factorial plus x to the 4 over 4 factorial plus x to the 5 over 5 factorial. So it's not a perfect approximation of e to the x, but it's better than just having a tangent line. And to see this in action a little bit, let's go ahead and plug in 0.2 and see what we get. So if we plug 0.2 into this, let me just go ahead and copy down all the denominators. So all the denominators, let's just write these quickly. And then let me go ahead and plug in 0.2 into the numerators. So this is going to be 0.2. This will be 0.2 squared. This will be 0.2 cubed, 0.2 to the 4th, and then 0.2 to the 5th. All right, so if we were to work this out, the right-hand side, and for this, we would need a calculator to do this, but a calculator can handle multiplication and division and addition really quickly. A calculator will tell us that this is approximately equal to 1.22140267. So let's compare that to what a calculator tells us the left-hand side is. Because a calculator uses stuff like this, although it might use a more accurate approximation. So a calculator will tell us that this is approximately, e to the 0.2 is approximately 1.221402. So far it's the same, and then 76. And then there will be some more decimal digits after that. So that is a really good approximation. It was good up until the first 6 decimal spots, and that's where it differed. So even just getting a 5th degree polynomial gave us a really close approximation. One of the reasons why, beyond the fact that higher degree means we get a better approximation, is the fact that the number that we were plugging in, 0.2, was really close if we go back to the picture. So if we go back to the picture, 0.2 is really close to where 0 is in this picture. In general, the further away something like 0.2 was, like if we were to pick something like 100 to plug in, that would give us a much worse approximation, because that's so far away from 0. All right, so going back to where we were, So in general, when we use this sort of polynomial to approximate what e to the 0.2 is, I won't know what e to the 0.2 is ahead of time. So we'd like to be able to get an idea of, well, how good is this 1.22140267, this first number that I got? How close is that to the actual value, even if I don't know what the actual value is? And we can determine that. We can determine how good of an estimate we have without knowing e to the 0.2 what it is exactly. And we'll talk about how to do that in the next section, so in section 10.9. All right, so there's a Desmos demonstration that I want to do to show you graphically what this polynomial approximation looks like and how good of an approximation to e to the x it is. But I'm going to save that for the following video. So I want to end with just a more general definition. So this is the definition of the nth Taylor polynomial of a function f of x at a. So the definition for that is, I'm going to call this Pn of x to indicate its degree n, and it has a form that's really similar to the form of this polynomial that we just got for e to the x. You have the value of the function in the front, f of a, plus the first derivative evaluated at a times x minus a over 1 factorial. That's kind of like this term. And then you have the second derivative evaluated at a times x minus a squared over 2 factorial. That's like this term right here. It's the analog of that. And I keep going up until I get to the nth degree term. I just take the nth derivative of f, I plug in a, multiply that by x minus a to the n over n factorial. So in the example that we just did with e to the x, all of these values like f of a, f prime of a, f double prime of a, all of those were 1. That's why in the numerator, all these coefficients are just 1. This is technically 1x and 1x squared. And that happened up here. That we had all of these 1s when we plugged in to our function and its derivative. Okay, so this is matching up with what we just got. It's just a more general formula. Okay, so these Taylor polynomials approximate our function near x equals a, whatever that value is. And the reason why is because the Taylor polynomials agree with the function at a, starting with the original function, plugging a into f, and plugging a into the Taylor polynomial. And it also agrees on the first n derivatives. That's why it leads to this good approximation. So in the next video, we're going to take a look at what a Taylor series is. And with the Taylor series, we're going to make this into an infinite polynomial.